it's a cooperation between the system designers and the microprocessor designers. It allows us to optimize and deliver the highest level of capability to the customer. In what we are offering today, if you look at the characteristics of the box, you will find high number of threads, large memory footprint. These boxes in the 1U are capable of 16 DIMM slots, which using 4 gigabyte DIMMs translates to 64 gigabytes of memory, and in the 2U configuration, where we can scale memory and I/O to higher levels, we achieve 128 gigabytes of memory in a 2U form factor. And that, of course, is using 4 gigabyte DIMMs. With next generation 8 gigabyte DIMMs, we'll be able to double that capacity to 128 and 256 respectively. The boxes not only require a balanced amount of CPU and memory capability, but you need to bring the data out or back into the system, and they're well balanced by in a number of ways. We have 3 and 6 slots of PCI Express I/O in the 1U and 2U respectively. Both systems have 4 gigabit Ethernet connections, as well as built-in 2 10 gigabit Ethernet ports. In the front of the box, we can scale the disk storage from anywhere from 4 to 16 drives, with capacities ranging from 73 gigabytes and 15K RPM devices all the way up to 146 gigabyte 10K drives. So delivering approximately in excess of 2 terabytes of storage right in the box. So the box also has built-in RAID capability, RAID 0 and 1, and of course by adding PCI Express adapters, we can achieve hardware RAID at levels 5 and 6. If you're not interested in that, obviously, we are able to running ZFS, the ZFS file system, which gives you far more capability and with respect to the storage that's in the box.
So I'm just astounded looking at some of these benchmark numbers that we have based on today's announcement. We are basically have outstanding numbers compared to much larger competitive systems, essentially rack-level systems. So what we're able to do here is a massive compression of the data center in terms of minimizing, the compute, I/O, memory capacities into a very small package relative to what our competitors can do. Masood, what were the design challenges, and how did you guys do this? It's incredible.
Well, I mean, a lot of the integration actually starts with the processor. There's the memory controllers are already built in. The I/O ports are built into the microprocessor, and as a result of that removes. There's far more tightly integrated, and it removes a lot of the issues that you deal with in systems design, and it leaves space for addition of other capabilities that were previously not possible. So the challenge here, obviously, is if you open up one of these boxes, you'll find that it's chock full of nuts, not any empty space. So to feed the microprocessor and gain the deliver on its performance capabilities, you have to have large memory footprint and I/O capability. And the challenge in fitting all of these devices into a 2U box with that amount of storage, obviously, is management of the heat that the product will, any electronic product generates. And if you look at the box, you'll see quite a bit of attention paid to heat management and with direct airflow front to back of the box, and it's really very efficient. So that's one of the challenges. The other challenge that we faced in designing these boxes, although today are being introduced as the new multi-socket CMT rack mount boxes, If you look at predecessor, which would be the T5120, the Niagara 2 base box that was announced in the last quarter of last year, it shares the same common chassis components and the chassis itself. In addition to that, these boxes are shared between us and the x86 side of the house. So you will be able to order machines that look very similar to these machines, with the only difference being the motherboard, which delivers the x86 instruction set. So getting everybody's requirement in and delivering a package that meets the performance needs, delivers it on the promises of the performance of the box, and the needs of the various markets that it goes into was another one of the challenges in delivering this box.
Right, and so from a chassis design perspective, as a sysadmin who's going to deploy some of these boxes, having a mixed environment is no longer really an issue. Essentially, we've got platforms with different architectures for different operating system and application environments. Yet when it comes to the deployment end, a lot of those hassles and complications seem to be reduced now, right? If it's a UltraSPARC-based system or a x86-based system, if I've learned on one box where to plug in the power and the network and serial ports and what have you, it's going to be the same across the board, isn't it?
That you're absolutely correct. The integrated lights-out management that we have built into these systems is identical to the x64, so it's identical across the latest generation of CMT line, the Niagara 2 base systems, as well as the Niagara 2 Plus, and the x64 system. So look and feel is exactly the same. The units are managed exactly the same, identical commands. And to go actually a step further, you will find that in our blade-based implementations of these architectures, we also have the same common management infrastructure.
That's great. So obviously one of the other design goals of the systems and the microprocessors was for the whole ecological aspect of computing. You touched upon some of the power and cooling benefits. At the system level, Rick, maybe you could talk a little bit about how we play in the eco-innovation here at the processor level.
Sure, Marshall. Yeah, as I mentioned earlier, the inherent architecture of our threading model and the multiple use of a common core across a number of virtually assigned threads is the beginnings, the actual underpinnings of the power efficiency of Niagara processors. That coupled with an operating system that coordinates power efficiency as it schedules threads across the core. So in a lightly loaded period of time, throughout the day, there are peaks and there are ebbs and flows of activity. And during the lightly loaded periods, Solaris will coagulate cores onto a single core and then have the ability of disabling cores, and thereby reducing the power consumption through those light periods of time. There are an abundant amount of power-saving techniques that were employed on the Niagara T2 processor, and again, we incorporated those. That extensive clock gating in the core, so if there is a functional unit that's not being activated, the clocks are disabled to that, and clocks tend to cause the power consumption to increase. So those are the features that we've deployed.
That's great. So it sounds like we've got, obviously we've innovated at the silicon level all the way to the box level and through software. Clearly, we are, one of the only, if not the only, vendor who has this level of innovation at all levels of the computing stack, which is really what's going to be required to deliver solutions to solve the customer needs of today and going forward. I mean, with these platforms that Rick and Masood have put together based on the UltraSPARC T2 Plus processor, with these heavily threaded and well-balanced systems in terms of memory and I/O, they're well suited to consolidate existing application environments as well as through virtualization and what have you. But it also opens up a whole new realm of opportunity going forward for developers to write applications which we may not even have conceptualized today. One of the things we've seen in the past with the UltraSPARC T1 based systems was a bit of some areas of less than optimal performance. And what I like to hear from Rick is, what were those improvements we've made over the generations of processors?
Sure.
And the second part of the question is this a general-purpose computing platform?
Yeah. Let's take the first question. What improvements have we made? Recall back in Niagara 1, the UltraSPARC T1 had one single floating point that was shared across the 32 threads. It provided at least floating point capability, but it became a bottleneck if there was a floating point content, let's say above 1, 2, 3%, something in that range. So with the introduction of the T2 processor last August, we embellished floating point to 1 floating point unit per core, and then if that was adopted in the T2 Plus, and so that gives you, from a system point of view, 16 fully pipelined floating point units shared across those 128 threads. And that capability, so not just having floating point units there is one thing. Having the ability with an enormous amount of memory bandwidth to feed those floating point units is really the key here. And I think if you look at our benchmark, spec FP rate would be one that you'd have to pay attention to and take a look at that. We scale quite nicely across all of those floating point units.
Okay. Great.
There was a second part, Marshall, but
the second part was, is this a general purpose?
Is it a general purpose? If you include every possible computing paradigm within that definition of general purpose, I would say no. I would say it's for commercially threaded applications, which is a wide swath of applications. It isn't a niche. So we're saying web infrastructure, database, job application servers, and HPC. I think this would be a very successful box in a technical market.
Okay, great. So all the buzz today seems to be about virtualization and consolidation. Obviously, these are key platforms to enable use of those technologies. Tell us a little bit about how we really have, this is the third generation of essentially embedded zero-cost virtualization we've incorporated into these processors and systems. Tell us a little bit about that.
Sure. So as we introduced Niagara several years ago, Niagara contained the capabilities of supporting a hypervisor, which is a very thin layer of software that exists between the underlying hardware and the operating system. Operating systems essentially can be a guest upon that hypervisor. So that's how we started out, and upon that hypervisor, we built a logical domains platform. And so logical domains allows you to carve up the hardware into individual domains, and we can support as many domains as we have threads. So we can support up to 128 unique domains, each having their own operating system, instance of operating system, running on those 128 threads. And then on top of that, of course, containers within Solaris allows you to do OS virtualization and have a number of independent domains established as a zone. So we have very extensive virtualization capabilities. We do call it para-virtualization as well. So it isn't. We don't really virtualize below the thread itself, but we virtualize to the point of a thread. So there's always some, let's say, physical attribute, physical underlying attribute for a particular thread or a domain. Okay.
Great. And then we've also incorporated several more cryptographic functions into these processors. So essentially, it sounds like, with the higher needs for and sensitivity around data and encryption, that there's really no reason why a customer wouldn't utilize these in transfer files, through encryption and in a secure manner. Is there any? What's the overhead, if any, with that?
Well, we have cryptographic coprocessors that are sprinkled out. There's one instantiated per core. So if you look at these these systems that we're introducing today, we have 16 independent cryptographic coprocessing elements per system. And since they are coprocessors, a thread could spawn a bulk cipher, either encrypt or decrypt, and allow that core to continue executing applications on the other thread. So it doesn't busy up the thread itself, the critical component that is the core itself, with an encryption function. So from that point of view, we are saying it's zero cost from the point of view of processors now being able to continue on executing applications for other threads, other domains as they're assigned. So we target about 5 gigabytes per instance, 5 gigabytes of, let's say, encrypt bandwidth. And for things like AES 128, we're probably a little bit under that in the bulk encryption decrypt for AES 128.
Great. So it sounds like we've got a lot of added functionality. We've talked about the system performance and other features. Clearly, these are platforms designed to, run everything from, HPC, back office, database, web applications, fairly wide variety of highly important and business-critical applications. So obviously, one of the major issues for customers is going to be reliability, availability, and serviceability. Masood, can you talk a little bit about what we've done in terms of system design to ensure maximum uptime on these boxes and the serviceability features?
Sure. Probably it's best that we start from the front of the box. As you see in the front of the box, there are a large number of disk drives that the chassis can accommodate. Disk drives inherently don't like vibration. They don't like vibration, rotational vibration from their partners and neighbors, and they don't like the vibration that's caused purely by the existence of fans within the chassis, which is required to cool the system. So if you look at these boxes, you will find that they're designed in really 3 main sections, with the front section being the disk housing that is isolated from the rest of the chassis with material that dampens vibration. If you look at the fan housing, which are hot plugged and hot swappable, you will find material around the corners of the fan assembly that is again dampening material that isolates them from the rest of the box and minimizes the disruption and the propagation of vibration into the disks. Vibration of the disks don't like vibration because it just reduces their life over time or impacts their performance. Other features, as I've mentioned, the ability to have redundant hot swappable fans. We, in addition to that, have redundant and hot swappable, highly efficient power supplies. The fully configured systems are capable of running on a single power supply. The second power supply is in place to provide redundancy. At 50% of the load, which is when what a power supply would run with redundancy built into the system, and at max load of the system, the efficiency is north of 90%. So that means that the conversion process from AC to DC is efficient and generates less heat. Other things that are built into the box that improve reliability. Actually, it's more availability at the box at the solution level. Obviously, is the fact that there are redundant paths and redundant I/O slots, so the system can be configured for redundancy and resiliency. But the fundamental piece that adds to the reliability of the box indeed is the fact that very much has been integrated onto the microprocessor. And that means fewer components. Fewer components means more reliability. So these boxes are pretty reliable systems by virtue of that.
Great. So, just to wrap up here, first I want to, thank Rick and Masood. It's been a pleasure and a privilege to have the two leaders of the teams who've developed and innovated the chips and the systems here. So thank you very much for being here. This has been a joy. And
my pleasure, Marshall.
Before we move to a quick Q&A, I just wanted to leave the audience with my thanks as well as two takeaways. One is, if you'd like to get more in-depth architectural technical information on our CMT line of servers, please visit wikis.sun.com/display/CMT and join the architectural community there and participate. And secondly, if you're interested in doing a quick risk-free evaluation of these systems, go to sun.com/tryandbuy.
Gentlemen, thanks very much. We had a number of questions from the audience, as I believe you saw, and if we could start with some of those, that would be great. Looking back, popping the conversation back somewhat to the beginning, I'm not certain whether this question was answered, but is a 6340 blade expected?
Yes. You can expect a blade implementation of this technology probably the second half of this calendar year.
Okay. Several people asked about that.
Henceforth, I think it'd be safe for everybody to assume that we will offer the processor technology in different physical implementations, rack mount, and as well as blades. And to the best of our ability, we'll try to do those simultaneously. Sometimes not, due to other limitations of resources and people, they'll be paced. Sometimes you'll find the blade ahead of the rack mount box or the other way around.
Someone asked, I think it was Rick D, asked, he doesn't see the immediate value in housing drives locally. The data centers have valuable storage on big boxes. Presumably, because the new machines are available in a variety of drive setups and form factors, that's sort of anticipated by the fact that one can get low numbers of drives local to the machines. Is that the case? And is there other planning for network-attached and other centralized large-scale storage?
Yes, I mean, the model of storage hasn't changed, right? And you can still have large pools of storage sitting outside the box. With this box, we're integrating more local disks, and, depending on your application, some people will utilize those disks, and some may choose not to, and stay with, just a few slots internally and a few drives internally, and then you get all the rest of their data off of a SAN or a NAS. In a way, you could look at a 16 disk drive implementation of this technology as a mini thumper today.
Henry asks, is it correct that in order to leverage this new system, we have to use Solaris? And the follow-on question is, Oracle has selected Red Hat Unbreakable Linux for their platform of choice. How can Solaris become the choice platform for Oracle or SAP?
Yeah, so obviously the platform supports Solaris 10. And in addition to that, we support Linux on these boxes. It's Ubuntu Linux. It is not Red Hat Linux.
I'm sorry.
Yeah, go ahead.
No. Well, okay. LW asks, how does T2/T2 Plus perform with floating point apps like SPS or Stata?
Oh, we haven't really run those particular benchmarks, but I believe if you go to the spec.org site and check out spec FP rate, you can see the performance we do